Prove that the limit as h approaches 0 of cos h minus 1 over h equals 0 as part A. Part B, using the limit definition of the derivative, prove that if f of x equals sine x, then f dashed x equals cos x. Right, so we'll start with part A. So we are looking to find the lim as h approaches 0 of cos h minus 1 over h. Now, something like this, if you were to just substitute, think about the value of cos h as h approaches 0. Well, cos 0 is 1, so this bit's going to approach 1. So the numerator would approach 1 minus 1, which is 0. And we've been told h is approaching 0. So if we just blindly substituted, this would be 0 over 0, which is indeterminate. So that's why we need something else. So potentially, you might remember the other day, when you get something like this, we can use these difference of two. It's often a good thing just to do, is to multiply by a sort of something that looks a bit like a conjugate. We're making a difference of two squares, a situation. Going to multiply by cos h plus 1 over cos h plus 1, so like that. And what we're hoping to get to is a situation where we can use the fundamental trigonometric limits. All of these limits involving sine and cos. If we're proving stuff, we're looking to use that fundamental trigonometric limit, which is the limit as h approaches 0 of sine h over h, which is 1. Right, so if we look at this, on the top you've got a difference of two squares, so that'll be cos squared h minus 1. Now we have the lim as h approaches 0 of cos squared h minus 1 on the top. On the bottom we have h cos h plus 1, like that. Right. So remember, we're looking to use the fundamental trigonometric limit. You're going to need a sine. So once you get your cos squared, which is why we're doing this really, if we get a cos squared, then we can substitute to turn it into sine. Right. So I'm just going to write, instead of cos squared h, I'm going to use the Pythagorean identity. I'm going to say this cos squared h is 1 minus sine squared h. So lim as h approaches 0 of 1 minus sine squared h minus the other 1 over h cos h plus 1. Right, so the ones will cancel out, which is quite handy. So we then have minus sine squared h over h cos h plus 1. So now we have the lim as h approaches 0 of, so what I'm going to say is, well, it's minus, I'm going to leave the one of the minus signs on its own, so I'm going to turn this sine squared h into a sine h times another sine h. So I want to put one of the sine h's with this h, and that's going to get rid of the 0 off the bottom, because I can use the fundamental trigonometric limit. So I'm going to rewrite this minus sine squared h as sine h times minus sine h. So sine h over h. So I've pulled these two apart, times, and then you've still got on the top a minus sine h, and then we've got this cos h plus 1. Right. So now remember, we can use what we know, the limit of the product is the product of the limits. So if we can find this limit and this limit, then we just times them together. This first one, the limit as h approaches 0, sine h over h, is 1, fundamental trigonometric limit, times, well, here, as h approaches 0, sine h or minus sine h will both approach 0. So 0 on the top, and on the bottom, well, as h approaches 0, cos h will approach 1, so cos h plus 1 will approach 2. And now this limit is not indeterminate. 0 divided by something is absolutely fine. Right, so now we've shown that it's 0 as required. Part B, we now need to use the limit definition of the derivative. So the limit definition of the derivative, which is in the formula book, just in the main bit, not even the option bit, is that f dashed x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So in f dash to x, using the limit definition, equals the limit as h approaches 0 of f of x plus h. So f of x is sine x, so would it be sine x plus h minus f of x, that would be sine x, all over h. Right, so when you get something like this, what you want to do is go to your compound angle rules about sine. So hopefully you can find it, or you remember that sine a plus b equals sine a cos b plus cos a sine b. So that's just using the compound angle, but I'm not going to write the whole thing down, I'll just write it in this context, but we're using the compound angle rules. So now we have the limit as h approaches 0 of, remember, sine a cos b, so that would be sine x cos h, sine x cos h plus cos x sine h minus sine x, all of that over the h. Right, now this is tricky, but what we're looking to do is we're looking to get to situations where we can use the fundamental trigonometric limit, and whenever you get a multi-part question, always think, is the result in the previous question going to be any use here? So don't forget, but this question is put together for a reason. So this limit that we found, the limit as h approaches 0 of cos h minus 1 over h, wouldn't just be there and then not have any relevance to part b at all. We're looking, this is something we can use. If we can get an expression that looks like this in here, then we can use this limit that we've found already. And also we've always got the fundamental trigonometric limit up our sleeve. So looking at this top line, all we can immediately do really is take a common factor of sine x out of these two terms. There's nothing else, there's no other common factor in there, so that's got to be literally the only thing we can do, so let's do that. So equals lim as h approaches 0, so I'm going to pull a sine x out, sine x, and then we have cos h minus 1. That's the first term and the third term, and then we've still got the second term there, plus cos x sine h all over h. Right, so now we're actually getting somewhere. So what we can do now is we can try and, you've got two separate terms. This one here, remember, this is the limit as h approaches 0 of the first term over h plus the second term over h. So we've got to put an h with both of these, and we can pull them apart even further, because if we put the h with this bit, the cos h minus 1, well, that's exactly the limit we found in part A. If we put the h with the sine h, well, that's the fundamental trigonometric limit. So now we're really getting somewhere. So this now equals the lim as h approaches 0 of, well, it's sine x times cos h minus 1 over h, and I won't put a bracket, or I will put a bracket just to make it easier, plus, it's a limit of all of this, by the way, plus cos x times, and then you've got sine h over h, and it's the limit of all of that. Right, so now we can use our limit laws, and we know that the limit of the sums is the sums of the limits, so we can find the limit of this separately, and also the limit of the products is the product of the limits. Now if you're thinking, well, what's the limit as h approaches 0 of sine x? Well, it's just sine x, because h is approaching 0. It doesn't say anything about what x is doing, so the sine x doesn't vary at all as h varies. It's just sine x. Just think back to your first principles, which is actually what this is. So this now becomes sine x times, and then we've got the limit as h approaches 0 of cos h minus 1 over h, which was the question in part A, which was shown is 0, plus, again in the same way, cos x as h approaches 0, cos x just approaches cos x, which is completely independent of h, cos x times, and then we've got the limit as h approaches 0 of sine h over h, which is 1, because it's the fundamental trigonometric limit, 1. So now we have sine x times 0 is 0, cos x times 1 is cos x. Okay, therefore, we've now shown, therefore, if f of x equals sine x, f dashed x equals cos x. So that is a standard result that I'm sure you know, and we have just differentiated sin x by first principles to prove that it is so.